Hi folks, tonight's review is for Calc 1, and I just want to point out there's a chat box over on the side. If you have any questions, please just ask them along the way, and I'll try and solve them. I might even make some time, move a problem around or two, unless it's coming up later. I'll be happy to answer those right away. So please ask questions, that's the main reason I'm here. And so without further ado, I'll get started. We're going to start with some limit problems, then go on to some derivative problems, integration. I think we cover related rates and optimization, and so on and so forth. So just trying to cover a wide array of topics that were covered in Calc 1. So without further ado, let's get started with limits. And so we have evaluate the following limits. The limit as x approaches 5 of x squared minus 7x plus 10 divided by x cubed minus 125. So the first thing to do when we're trying a problem like this is to plug in. And so there's a couple ways to approach this, and so we'll go through one. You notice you have 0 over 0, so that means one route that we might remember from before is to actually factor this thing. So you can factor it. The top has a factor of x minus 5, and the bottom has a factor of x minus 5. In the top case, we have x minus 5 and x minus 2 would be our other factor. And for x cubed minus 125, that's actually a perfect cube. And so we can rewrite that as x squared, and then I believe it goes plus 5x and then plus 25. And you can check to see that that matches to x cubed minus 125. So now where do we go from here? Well, let's take a look and see what happens. So we can cancel off our x minus 5's, and we're left with the limit as x approaches 5 of x minus 2, and then we have x squared plus 5x plus 25. And so what does that make now? Well, we get 3 on top, and down below plug in 5, so we get 5 squared is 25 plus another 25 plus another 25. That should make 75. And notice 3 over 75 we can just reduce down to 1 over 25, and that's our final answer. But that's not our only route. Notice when we had 0 over 0, that's an indeterminate form, so we could have used L'Hopital's rule, and we could have rewritten this as limit as x approaches 5 of, well, we take derivatives. So we get 2x minus 7 up top as our derivative, and down below we get 3x squared, because the constants are, the derivative of a constant is 0. So using those kind of notions, we can plug in 5. And so notice we get 3 up top, and then 3 times 5 squared. Notice you square the 5 first, so that's going to be 25 times 3 is 75. And so 3 over 75 is just 1 over 25. And so two different ways to approach the same problem. And you can kind of pick and choose whichever one works for you. A lot of people like L'Hopital's rule, and it does come in handy quite a bit. So just be aware of how to use that thing. Now, moving forward to the next one. Say we have the limit as x approaches 0 from the right of sine of x raised to the 2x power. You plug this in, you get 0 raised to the 0 power. What the heck does that mean? So we got to figure out a better way to approach it. And the thing that makes this troublesome is this 2x up in the exponent. And so how do we handle that? Well, we do this e raised to the natural log of the limit. So I'll actually just put the limit out in front and save an extra writing piece. But so we do natural log of sine of x and then raised to the 2x. Okay. Now, one little caveat, the reason why we can get away with this, with the e and the natural log, they basically cancel out with one another. And so this becomes the same, it's still equal to sine of x raised to the 2x. So you can't just toss a natural log in without having the e involved down as the base of the exponent. Now, what does the natural log do for us, though? Well, that allows us to bring the power down. So we get e, and the limit as x approaches 0 from the right of 2x and then natural log of sine x. Okay? And now where do we go from here? Well, we can pull the 2 out in front. That's not going to do any harm. So this is e, and then we have a 2 right here, and then we have a limit as x approaches 0 from the right of. Now, as plugging in right here, you have 0 times natural log of essentially 0, which would be approaching negative infinity. That's an indeterminate form, but not the format that we want. So we got to fix that. And there's a simple fix to do this. We already pulled the 2 out in front, so that means we just have the x left involved. So what we'll do is we'll write this as 1 over x. Because notice when you divide by that fraction, you multiply by its reciprocal, which goes back to x times natural log of sine of x. So with that in mind, we do have an indeterminate form now, because as we approach 0 from the right, what happens here? Well, this is approaching negative infinity essentially up top, and down below, as we approach 0 from the right, we get positive infinity. So you have an indeterminate form, so we can use L'Hopital's rule. That's important, so I'll just put L'Hopital's rule once again. It'll be a common theme, not all the time, but for a lot of the problems with limits, it can make life easy. So this is limit as x approaches 0 from the right. Now remember, we take the derivative of the numerator and divide by the derivative of the denominator. Derivative of the numerator, we need to take the chain rule. So this goes 1 over sine of x times cosine x. And then for that other piece, we have 1 over x. That's negative 1 over x squared. Wowzers. Well, notice though, cosine of 0 is actually a nice value, and we can kind of rewrite this. So e, and then we'll have the 2, and then notice there's a negative symbol with the 1 over x squared, so I'll make it negative 2, and then we'll put the limit as x approaches 0 from the right. We'll deal with the cosine x separately, just because we can already plug that in. And then we have the limit as x approaches 0 from the right of, we can write x squared divided by sine of x. So this is quite a bit of work, but let you see what's happening here. So the part where we have limit as x approaches 0 from the right of cosine of x, that's just 1. You get cosine of 0 is 1, so there's not much happening there. So we have e to the negative 2, limit as x approaches 0 from the right of, now when you plug in 0 into both of these, you get 0 over 0 again. So we can use L'Hopital's rule once more. And that gives us 2x over cosine x. And so now we're finally at a place where we can get a nice answer for ourselves. And so taking a look at this now, what actually happens? Well, we have plug in 0. And notice you'll get 0 divided by 1, which is 0. So this is e to the 0, and e to the 0 is 1. And that is our final answer. So hopefully that makes sense on that one. All right, moving forward to the next limit. So this is one where L'Hopital's rule will not come into play. And actually, if you try L'Hopital's rule, you're just going to run into more and more problems. These infinite limits, when we take a look at this, if you plug in infinity, you get infinity, and the other one goes infinity minus infinity. What the heck does that mean? So there's other ways to write this, and by the way, you can factor out an x here, and then you go x minus 4, so this goes infinity times infinity. So you have infinity minus infinity. That's an indeterminate form, so we have to do some work here. And the way we actually solve this type of problem is we multiply by the conjugate, but you can't just toss in a conjugate willy-nilly. You have to do a little bit of work. And what do I mean by that? Well, we can multiply by 1 all the time. And that's what we're going to do here. We're going to multiply by 1, but the way our 1's look might be just slightly different. And so what we have here is this is 1, right? Just written differently. And what does that allow us to do? Well, you can multiply those two, and just keep in mind, the reason why we're doing this is a minus b times a plus b equals a squared minus b squared, right? So that means that this limit actually becomes something much nicer. So up in the numerator now, we can square that square root, that first square root. So when you square that square root, it goes away and you're left with x squared plus 9x. Then minus you square the second square root, so it gets rid of the square root. So you have x squared minus 4x. That's the whole reason for this conjugation. You're just getting rid of the square roots. That's what makes the problem difficult here. If we didn't have them, it'd be a lot easier to work with. And then we have square root of x squared plus 9x plus the square root of x squared minus 4x. So the x squareds, if you notice, those things cancel. 9x minus a negative 4x makes 13x. So this thing equals, the limit as x approaches infinity, of 13x over square root of x squared plus 9x plus square root of x squared minus 4x. And I'll tell you what I see a lot of times with this is people try and use L'Hopital's rule. They run into trouble with that because actually it'll just make the problem more and more complicated. So this is a case where we want to avoid L'Hopital's rule. So how do we approach it? There's a few ways, and you'll see in videos, in the books. Each one has their own unique thing. What I like to use, not saying that you have to use this, is I find what the degree of the denominator is. Now the degree of the denominator, this might be tricky. You see the 2 here in front of the x squared. So that seems to be the degree, but you're taking the square root of that. So the square root of a square, that just basically goes back to 1. So what we'll do is we'll go by 1 over x to the first power, because that's essentially what the denominator is behaving like. So we'll multiply both the numerator and denominator by 1 over x. But the one caveat when we write this, that 1 over x in the bottom is the same as square root of 1 over x squared. That's what that is looking like, because when you take x squared and you square root it, you basically get x when we're dealing with positive values. For negative, it gets a little bit different and a little bit tricky in those cases, but for the positive values, that's what you're looking at. So what we have is the limit as x approaches infinity. Well, 13x times 1 over x just leaves us with 13, so that's not so bad. Now we have to multiply that 1 over x squared to each part. So 1 over x squared times x squared will just leave us with 1 in the first case, and 9x times 1 over x squared, that'll leave us with, what will we have? We'll have 9 over x, and then plus another square root. 1 over x squared times x squared is once again 1, and then minus 4x over x squared, that'll leave us with minus 4 over x. Okay, so no questions thus far. So now we'll just plug in that limit as x approaches infinity. There's no x's up top. But this thing, 9 over x, as x goes to infinity, so as x gets really, really large, think of 9 over a million, 9 over a billion, 9 over a trillion, that thing's going to 0 really fast. And same thing here, 4 over x, that's, well, I shouldn't say really fast, but faster than most things go to 0. So what we're left with is 13 over the square root of 1 plus the square root of 1. And I don't know much, but I can do the square root of 1. That's just 1. So this is 13 over 2, and that is our final answer right there. Okay, on to our next one. Limit as x approaches infinity of x to the 100th power over e to the x. So this one's kind of scary. When you plug them in, you get infinity over infinity. And what this is trying to do is see which one goes to infinity faster. That's essentially what these limits are kind of telling us. So in this case, I'll actually write it down below, we can use L'Hopital's rule. Right? The previous one, notice we didn't. So that was one of the cases where we didn't. A lot of them you can, though. But I tell people, try not to get too L-hop happy, because there are limits like that previous one that you can't do. Use that rule. So the derivative of x to the 100th is 100x to the 99th, just by the power rule. And the derivative of e to the x is just e to the x. Okay? Well, notice you plug in infinity again, you get infinity over infinity. Oh boy, so we got to use L'Hopital's rule again, because we had infinity over infinity, another indeterminate form. So we get this again, we do limit as x approaches infinity. Notice we get 100 times 99 times x to the 98. All over. Well, what do you know? It's e to the x again. Well, notice what's happening to the x power. The x power is decreasing by 1 every time, and you're multiplying by that power, essentially. So what happens is you can continue this process, so on and so forth, and if you need some help here, let me know. Happy to answer whatever questions you have. But so you continue this process until you get x to the 0, right? X to the 0 is just 1, so you've gone 100 times 99 times 98 times 97. An easier way for us to write that is just 100 factorial. over e to the x. Now notice, 100 factorial is a huge number. If you try and plug it into a calculator, you might get it to crash. We'll find out if you want to test it out. But e to the x, as x goes to infinity, it just keeps on getting larger and larger and larger. There's some point when it passes 100 factorial, and it keeps on getting larger as you plug in larger values. So what happens to this is, even though it seems like that's a large number, it doesn't matter. This thing still goes to 0. So that just kind of shows you the power limits. By the way, this last one actually shows up in Calc 2 quite frequently. You're trying to see rate is which things are going to 0 faster, and how fast are they actually going to 0. That's quite important. So moving forward, we're on to derivatives. So how do we take these derivatives? Well, a lot of these, just basically remembering your rules. As soon as you remember your rules, you're in pretty good shape. So in our first case, notice we have a product of two functions. There's the first function, there's the second function. And so what this is we have to use a product rule. And so our f prime of x, if you notice, it's going to be the derivative of that first function, e to the 7x, times the natural log of sine of x, plus e to the 7x times the derivative of the natural log of sine of x. And now, if you take a look at this, derivative of e to the 7x is e to the 7x, and then we have to use a chain rule. So derivative of that 7x, and then we have times natural log of sine of x, plus our second case is e to the 7x, and then we have natural log of sine of x, so that goes 1 over sine of x, is how that works, times, using the chain rule, once again, the derivative of sine of x. Okay, so now we have an equals there. We have just that derivative is 7, so I'll just pull that out in front. 7e to the 7x, natural log of sine of x, plus e to the 7x over derivative of sine is cosine. I'll just put that up top. Cosine x over sine of x, or a better way to have written that is just cotangent of x. And so if you want to jump to that step, go for it. That's awesome. If not, no big deal. This is a fine answer just as well, right? All of them work out the same. So that's how you take the derivative. And the same rules apply for our next one. You're going to have to use the chain rule. So when we find g prime of x, now some of you might know that formula for the square root, some of you might not. So just to make sure, I'm going to write this a different way. I'm going to write it as secant of x cubed plus 9x squared, all raised to the 1/2 power. So using the chain rule, this goes 1/2, and then you're using the power rule to start. So 1/2, then you have the inside, so secant of x cubed plus 9x squared, raised to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside. Well, the derivative of secant is secant tangent, so we'll write secant, and I'll leave a space, and then tangent, and I'll leave a space, and we'll fill that in with what we need. So that what we need is x cubed plus 9x squared in both spots. Okay, and then times the derivative of the inside. Now notice the other thing, it's the whole inside, x cubed plus 9x squared. I don't want to just write it without parentheses. I need that parentheses there because we're multiplying these derivatives when we use our chain rule. So we get 3x squared plus 18x, and then we close it off. Now you can brush this up if you want. It's not necessary, but some people like it that way. So if you wanted to, you can rewrite this. We can put it over one big fraction. You have a 2 down below. That negative 1/2 means it's down below. So you have a square root of secant of x cubed plus 9x squared. And then you have a secant of x cubed plus 9x squared tangent x cubed plus 9x squared. Let me bracket that off just so we can see here. And then we have a 3x squared plus 18x. And we fit it all in there. Good. You can do some more simplifying with that square root of secant x cubed plus 9x squared and the secant of x cubed plus 9x squared up in the numerator. But it's not necessary once again. You could have even left it at the previous term. That works just as well. Okay, our next one. There's a couple ways to do this. We'll focus on just the quotient rule because that'll be something that we haven't done yet, I should say. So the first thing you do when you use the quotient rule is you square that denominator. Now, you let that denominator rest. So the x to the fourth minus 7, and take the derivative of the numerator. Derivative of the numerator is just secant squared of x minus, since the numerator and denominator do not like each other, that's why we do that. And then from there, we rewrite our numerator, so tangent of x, and times the derivative of our denominator, which is, in this case, 4x cubed. So you might hear you square the denominator, then you go low d high, meaning the derivative of the higher function, minus high d low meaning the derivative of the lower function. So that's a pretty common sort of phrase that you hear over and over again. Yeah, you could probably brush this up a little bit. Well, not too much, but enough. But this is fine. Just leave it that way and you're good to go. So now, moving on to the next bit, let's take a look at this one. It has a couple of things that throw people for a loop. So first off, the 9 over x cubed, that's 9 times x to the negative 3. And then we can write plus the arctangent of e to the x. Okay, so when we take the derivative of this thing, use the power rule in that first case, even though it didn't look like it. A lot of people start doing some funky stuff with natural logs and things like that. It's not necessary here. So just use your power rule. You get negative 27x to the negative 4 plus, okay, derivative of arctangent. It goes 1 over 1 plus, it's usually x squared, but in this case we have e to the x is what we're squaring. And then times the derivative of the interior function, which is e to the x. So an easier way to have written this is negative 27 over x to the fourth plus e to the x over 1 plus e to the 2x. And that's a nice final answer right there. Now, last but certainly not least, this is the fundamental theorem of calculus part 1, the most often forgotten fundamental theorem of calculus. So you would think fundamental theorem of calculus is probably pretty important. You might want to star that. You need to know certain things about it. It does show up later on. We start defining functions in terms of integrals and things of that nature. You can try, in this case, and take an antiderivative. But if you know the fundamental theorem of calculus, part 1, especially in cases when you can't take the antiderivative, which happens more frequently than you might think, you need to work on setting this up. And what the fundamental theorem of calculus, part 1, says, it usually has an x up top, where you see this natural log of x to the 7th. But we can take this derivative quite simply. And here's all you need to do. So we have this negative symbol, so that's going to stay out in front. But the derivative, you're going to have sine of whatever goes in that variable as the top bound. So natural log of x to the 7th. And then times the derivative of that top bound. Well, notice this looks real tricky, but this is the same thing as derivative. Laws of logarithms, we don't even need to use. Just laws of logarithms says, hey, you know what? We can solve this just by using those laws and then using our derivatives of natural logs. So you can rewrite this as negative sine of natural log of x to the 7th times 7 over x. That's not a decimal there. And that's your final answer right there. Okay, with no other questions, let's move forward. Evaluate integrals. So we're evaluating the integrals here. How do we go about doing this? Well, first one. Let's rewrite the first part. It might be a little bit simpler. So we can write this as 5, and then we have x to the negative 3 dx plus an integral of secant squared x dx. So two separate integrals might be a little bit easier. This becomes 5. And now how do we actually take this antiderivative? It's kind of the reverse process of the power rule. So you get x to the negative 3 plus 1 over negative 3 plus 1. So that goes x to the negative 2 over negative 2 plus the antiderivative of secant squared. Well, the derivative of tangent of x is secant squared. We talked about that just a little bit ago. And then one last thing we always need to add in is a constant, because the derivative of a constant is 0, so when we're taking the antiderivative, we always put in this plus c business. So if we write this out a little bit nicer, you get negative 5 over 2x squared, then plus tan x plus c. Now as for our next one, we have this integral from negative pi over 2 to pi of absolute value of sine of x. So first off, I want to kind of discuss this a little bit. So what is sine doing? Well, sine kind of goes like this and like this over and over again. And then the period is usually 2 pi. But so we have at that high mark we have pi over 2, and on the low mark we have negative pi over 2, and then we'd have pi, and so on and so forth. So this would be f of x equals sine of x. So what's actually happened is, let me kind of highlight this, is this portion, and then obviously this portion over here as well, we basically flip it. And how do we flip it? We multiply by a negative 1. So what happens is this thing becomes the integral from negative pi over 2 to 0 of, well, if we're flipping this, it has to be negative sine of x dx plus the other breaking point. Notice we go from 0 to pi of just regular old sine of x dx. And that's essentially how we can tackle any absolute value. Just find where it's negative, and then as soon as you have that, you're in good shape. You're ready to solve this thing. So the antiderivative of negative sine of x should be positive cosine of x. So we have that integral becomes cosine of x from negative pi over 2 to 0. And then plus, well, our second one would be negative cosine of x. Is that antiderivative? Evaluated from 0 to pi. And so this thing equals, okay, I had a question before. Why is it 5 over negative 5 over 2x squared? I'll answer that along the way. Sorry, it just took me a second. I just saw it now. So moving back, I'll move back to that problem real quick along the way. So why is this and this equal, right? So let's take a look. Well, keep in mind x to the negative n is 1 over x to the nth power, right? And so when you have the 5, that 5, so if I had 5x to the negative n, notice that would be 5 times 1 over x to the n. And then that would mean we have 5 over x to the n, essentially. And so in our case, we have an x to the negative 2 up top. And that looks kind of scary, but notice what that becomes. Well, in our case, if you have x to the negative 2, that's just 1 over x squared according to that property. Okay? So with that being 1 over x squared, you have 5 times 1 over x squared, and then times the negative 2. So now this 1 over x squared can just drop down below. The negative symbol can come out in front, and then you get exactly what you see there. So does that make sense on that one? Just let me know if it does or does not. Hopefully that helped out. And keep those questions coming. That's exactly what I want to see. If you struggle on something along the way, just let me know. I keep on checking. I'm writing at times, so it takes me a couple seconds to recognize it. But once I do, I'll go back and solve that part. Okay, so going back, if I don't see any more questions on that one, hopefully you got that. If not, as I said, just let me know. So we have this integral where we have cosine x evaluated, so you have cosine of 0 minus cosine of negative pi over 2. So that's that first part that we've evaluated. Plus, our second part is negative cosine of pi minus a negative cosine of 0. Okay, cosine of 0 is 1. Cosine of negative pi over 2 is 0, so 1 minus 0. Cosine of pi is negative 1, so you get negative negative 1. Minus, and then cosine of 0 we already said is 1, so you get minus and minus 1. So notice we get 1, plus 1, another plus 1, so that makes 3 is our final answer on all that. So who'd have thought all the sine stuff becomes 3? Alright, with no more questions on those, we'll move forward to the next one. If not, just let me know. I can always scroll back and whatnot. So evaluate the following integrals. Now we have some trickier ones, and let's see how we handle this. So these are some of the trickier cases. These are U substitutions. And here, I'm actually going to do this incorrect right out the gate. So I want you to see what happens and how much you're out if you don't know what to do. So ideally, if we take a u equal to 1 plus 4 e to the 4x, because the fraction is what makes it look complicated, then we have du equals 4e to the 4x dx. Now, notice up top we have an e to the 2x sitting right up there. That does not match this e to the 4x. So we're going to have problems canceling that out. So this probably isn't our right choice. And that's what happens. You're out of a couple seconds if you make an incorrect guess. And so that's what we'll do. We'll just go back to the drawing board. Try another value of u. And so in this case, it does take a bit of practice, but e to the 2x, the derivative of that, is going to have an e to the 2x here. So notice if I use u equal to e to the 2x, we have du equals 2e to the 2x dx. And you might be saying, well, wait a second, there's an e to the 4x down below. So we're kind of stuck. Well, yes and no. I'm going to rewrite this just slightly. So notice this is e to the 2x over 1 plus e to the 2x, the quantity squared, dx. And so notice what you actually have is an integral of, let's rewrite. So some people like to do it where they just kind of catch what's matching. Other people like to write it this way where they solve for dx. So dx equals du over 2e to the 2x. Oops. Didn't need that extra dx there. So you get du over 2e to the 2x in that part. So we'd have e to the 2x 1 plus, now this e to the 2x, so let's write it as u squared. And the reason for that will become known in a second. And you have a du over 2e to the 2x. So notice what happens is we're allowed to cancel out this one and this one. And so what we're left with is then just an integral of du over 1 plus u squared. And so hopefully you recognize this one. You may or may not. It just happened on the previous page. We took a derivative of an arctangent. And that's exactly what this is. This is the arctangent of u plus some constant c. And so this is the arctangent of, well, we had e to the 2x plus a constant c. And that's your final answer on that one. On our last one, this is kind of tricky because of the cube root and that 5x minus 1. And so usually a good starting place is to go u equal to 5x minus 1. But notice then du equals 5 dx, or an easier way for some of us to see it is dx equals du divided by 5. If that's the case, notice we end up with an integral of x cube root of u and a du over 5. And you might say, oh, that just isn't going to work. But actually it does in this case. So this is one of those crazy scenarios, and you could have actually manipulated the previous one. You still come up with an arctangent of e to the 2x. It just would take a little bit more work. But sometimes we get creative with our u values and making these substitutions. So notice you have u plus 1 equals 5x. So in that case, we get u plus 1 over 5 equals x. So this integral, we can replace the x now with u plus 1 over 5, okay, times the cube root of u, and then times du over 5. So notice the 5 in the denominator of both those parts can be pulled out, so that's 1 over 25 times the integral of u plus 1, that whole quantity, times the cube root of u. Whoops, put the u up there. And then a du. Now how do we solve this one? This one scares people at times, so just distribute the cube root of u to both terms. And so we have 1 over 25 times the integral. It would be u to the 4/3 plus, and then I'll write the other one as just u to the 1/3, and then we have du. So now we use that opposite of the power rule, so you get 1 over 25 u to the 4/3, so you add 4/3, so that would be u to the 7/3, and then all divided by 7/3, which some of you might be more comfortable writing it in a simpler format, which we'll do here in a second. And then you add 1 to the second term, so that's u to the 4/3 divided by 4/3, okay, and all this goes plus c. So this thing becomes 1 over 25. Now we plug back in for u, and I'll kind of do the multiplying by the reciprocal because we're dividing by a fraction all in one step. So we have 3, our u value is 5x minus 1. So 3 times 5x minus 1 raised to the 7/3 all over 7 in that first case, plus 3, we'll have the 4 down below, and then we have 5x minus 1 raised to the 4/3, and then all that we take plus c. Just an FYI, you might see cube roots raised to the 7th and cube root raised to the 4th. That's different formats, all for the same thing is what we're representing there. So just keep that in mind. So there's the integrals. Hopefully you're pretty comfortable with these. You're going to see a ton of them come exam time, so I just want you to be prepared and just see the different flavors that you can get them in. Now let's go forward to using graphs. So use a graph of the function below to evaluate the given expressions. So we have the limit as x approaches -5 of f of x. So what do we do? Well, so -5, notice that's x equals -5. And then what I'll do is I'll kind of draw a dotted line. And so we approach from the left-hand side of the graph and from the right-hand side. Notice there's no mention when we're talking limits, we're approaching values. We don't care about the function, even though the function appears down below, right where I just circled. That doesn't make a difference. Unless you see an f of -5, it's not going to play a role here. So what y value are we approaching? Well, if you notice, the y value that we're approaching there is, that's up 1, 2, 3, 4. And so since it's up 4 units is where we're approaching, that's going to be +4 for that answer. Limit as x approaches -4. So notice we'll go over to the -4. Whoa, that was all sorts of messed up with my drawing there. So now, what happens? Well, if you look, if we're approaching from the left-hand side, we're approaching from the right-hand side, which value is it? Well, remember that a left-hand limit and a right-hand limit must be equal in order for a limit to exist. The left-hand limit in this case is like 2.5. The right-hand limit is 1. So this is a case of a does not exist scenario. Okay, so now limit as x approaches 4 from the right. So we go 4, and then we're approaching from the right. Okay, so now from the right hand side, we only care about this way. So in this case, what do you know? Kind of lucked out. It happened to be the same value that we had before, 4. I promise you not every answer is going to be equal to 4, by the way. So now the next one, f prime of 3. So what does that mean? Well, we draw a tangent line. So here's the point when x equals 3. And then we want to draw a tangent line. Well, that's going to be, since it is a line, the tangent line is the slope of that same line. Well, what is the slope? So here's the question. What is the slope of this line? If you know the slope of this line, you're good to go. And what is the slope when we have no rising or falling? Well, it's 0. So otherwise, just find 2 points and then do your y2 minus y1 divided by x2 minus x1. Okay, now on to our next part. The integral from -2 to 1 of f of x dx. Now notice this makes a nice shape. So we have going from here, and then there's 1 right there. So we want to shade this area in. And remember, it's a negative value. So when you take a look, what do we have? Well, the triangle here has height of 3. The base, 1, 2, and 3 is there. So this thing should equal, now remember it's negative because it's below the x-axis, 1/2 base times the height. So this equals -9/2. Now, on to the next part. Well, it might be easier for us because we have some parts that are below, some parts that are above. Break it up. So break up that integral. We're allowed to do that. Break it up into the part that's below, and then break it into the part that's above. So we go -2 to 1 of f of x dx, and then we'll go 1, 2, 4. We're actually probably looking at the shapes. I'll be honest with you. We probably even want to break it up even more so. Go from 1 to 2 f of x dx, and then plus 2 to 4 f of x dx. And why is that? Well, notice from 1 to 2, we have another triangle that's positive. And then from 2 to 4, what's happening? When we have a rectangle. So when we look at all these, excuse me, we already know the answer from the integral -2 to 1. That's -9/2. The triangle has a base of 1 and a height of 1. So this would be plus 1/2 times 1 times 1 plus a rectangle's area. It's just length times our width. So you have 2 times the 1. So plus 2 times 1. So notice this gives us -9/2 plus 1/2 plus 2. That's -8/2, which is -4 plus 2, which is equal to -2. And that is our final answer for that one. Alright, now let's get to some word problems. Related rates time. So let's say we have a TV camera is positioned 4,000 feet from the base of a rocket launching pad. So what I like to do is, what helps me at least, doesn't have to help you, whatever you prefer, and as long as it works, that's great. But so say we have a rocket launching pad. So there's the rocket launching pad. And then we have a television camera. Right here. Now, what we know, first off, is that this distance from here to here has to be 4,000 feet. Right? Now, I could have drawn the rocket if need be, but I think it's probably going to be moving. That's usually my guess here. So the angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. So the 4,000 feet, that's not changing. That's a constant. That's important here. However, the rocket is shooting up. So there's our rocket ship. So a rocket ship flying on up. Don't worry, that's a beautiful drawing of a rocket ship, just in case you didn't notice that yet. So the camera's trying to focus this in. So this height, which we'll call h, is changing. And then this distance here, which we'll call, I'll just call it L for length. Usually a lot of people like to use D, but D is going to be used for derivatives at times in these, so that's why I'll just use L instead. But if you want to use D, go for it. So those are some of the changing parts, and it also talks about focusing the camera, so you're talking an angle here as well. So this angle, let's call it theta. All of those are involved, they're in play for this problem. Now the givens, though, besides the 4,000, the givens that are changing, when h equals 3,000 feet, and let's assume the rocket rises vertically at 600 feet per second. So the first one, that was h according to our drawing, and then the second one we're going to have dh dt, and this would be 600 feet per second. So all that's just given in there. In our first problem, how fast is the distance from the television camera to the rocket changing at the moment? What we want to do is try and figure out what we're looking for. Well, in this case, what we're looking for, we're talking fast distance from the television camera to the rocket. So distance from the television camera, right, which is right in here, to the rocket is L. So in our case, with our drawing, this is dl dt. Okay, that's what we're looking for. So now let's break it down. What's an equation where we can involve L, H, and that 4,000? Well, notice this is a right triangle. So the easiest one I can think of is L squared plus, L squared, not plus, L squared equals H squared plus the 4,000 squared. Okay. That might come in handy in just a little bit. Now, the reason why we don't plug in right away is because L and H are changing their variables, so we need, when we take the derivatives, since we're looking for dl dt, those are things we have to account for. So we take d dt of L squared equals d dt of H squared, our derivative respect to t of 4,000 squared. Okay. What happens then? Well, we get 2L, then dl dt by implicit differentiation is what's going on there. And then 2h dh dt. So we can divide both sides by the 2L, and we get dl dt equals 2h over 2L and then dh dt. So this is just h over L dh dt. Now that's where we might get stuck, right? We don't have L. What is L? Well, that's where we can use our original formula. L squared equals 3,000 squared plus 4,000 squared. I don't know if you remember triangle, but the 3, 4, and 5 right triangle is one that comes to mind right now. And so that's what we're going to have. L, you can solve it if need be, but L will equal 5,000. So what does that mean at the end of the day? Well, that means that dl dt in our case, equals h over L. So h, what is it? Well, it's 3,000. L is 5,000. dh dt is 600. Okay, so you can cross off all those zeros, and the 5 goes into 600. You can think of it, it goes into 60, 12 times? So 5, 60, you'll have 120. So 3 times 120. So we have our answer. Sorry for the lack of room here, but I'll put it right up here. dl dt equals 3 times 120, which is 360, and it should be feet per second. Okay. Hopefully that made sense on that part. Now, if the TV camera is always kept aimed at the rocket, how fast is the camera's angle moving? we're looking for a relationship. Since we have h and dh dt, we want to probably drop the L in this case. You could work with it, but it's not really necessary. What we probably want to work with in this case is tangent. So the tangent of theta equals h over 4,000. So same thing, when we take the derivative with respect to t, right? So you get d dt of tangent theta equals d dt of h. Now think of this as 1 over 4,000 times h. That's an easier way to do it. You don't have to use a quotient rule or anything fancy like that. When we have this, we have secant squared theta d theta dt equals 1 over 4,000 dh dt. So now, moving forward from here, what's secant squared of theta? Well, notice that's 1 over cosine squared theta d theta dt. And by the way, I should have mentioned, I kind of jumped right into it, how fast is the camera's angle changing? So we're looking for d theta dt in this case. So this thing equals, we'll have that 1 over 4,000 dh dt. Well, an easier way to look at this now is just d theta dt equals cosine squared theta over 4,000 dh dt. What is cosine squared of theta? Well, we just found it's going to be adjacent over our hypotenuse. So our adjacent side is 4,000 over our hypotenuse is, we just found, it's 5,000 just a second ago, and all of that's over 4,000, and dh dt is 600. So this becomes 1 over 5,000 times 600. You can cross off those two zeros with two zeros below. And then, well, yeah, so you have 6 over 50, or that'd be 3 over 25. So this d theta dt equals 3 over 25. And this would be radians per, what is it, second? Yeah. And that's our final answer. So there's our good old related rates problems. Next one, moving on to optimization. So find the equation of a line through the point 9, 4 that cuts off the least area from the first quadrant. So what's happening there? What the heck is going on with this? So 9, 4, let's say 9's here, and then you have 4 here. I'm not saying this is to scale, but you can get a visual. Notice if we have anything with positive slope, it's not cutting off any area, right? Because it continues on forever and ever in the first quadrant, right? So the key is the first quadrant. So in order to draw this, what's happening is we can adjust it, but we're either having something like this, where that continues up, or you might have another line that maybe flat lines like this. But at the end, we're just trying to maximize this sort of area right here. Okay, and this is telling you, just by the drawing itself, you can get a visual of, if you have y equals mx plus b, you know for a fact that m is going to be having some negative slope. So if we're taking a look at this, another route that we might want to use, rather than y equals mx plus b, to be a little bit more precise, we have this 0.94. And what we might want to use, what might behoove us to use, is that point slope formula. So we have y minus 4 equals some m times x minus x1, which is 9. So in other words, if we wanted to write that, we can be a little bit more specific by writing y equals mx minus 9m, then plus some 4. Okay? So what does that mean now? We want to maximize the area, right? Or not maximize, I'm sorry, minimize the area. So if we're minimizing the area, we got to find a couple things. We got to find when does it cross the y-axis? And why is that? Well, that will tell us our height of our triangle. And then we also need to find where it crosses the x-axis. Why is that? Well, that will tell us our base. Okay, well, how do we find those things? Well, actually, those aren't too bad. To find where it crosses the y-axis, all we do is plug in x equal to 0. And what do we get? Well, we get y equals m times 0 minus 9m plus 4. And so then in that case, we get y equals negative 9m plus 4. Okay, that's good. Now, as for our base, what's happening? Well, that's an x-intercept. So what do? We plug in x equal to 0. And what do we have? Or not x equal to 0, my apologies. Y equal to 0. So you get 0 equals mx minus 9m plus 4. Notice we're solving for x in this case, so we get 9m minus 4 equals mx. So x equals 9m minus 4, all divided by m. Alright, now we're ready to rock and roll. And I'm going to, I'll try and fit it up here, and we'll kind of start, and maybe I'll move over to that other side. So our area equation will be in terms of m here, because it's our slope that we want first, and then we'll figure out the rest from there, because as soon as we have that, we get the rest for free. So area in terms of the m, the slope, will be, well, it goes 1/2 our base, which is 9m minus 4, all divided by m, times negative 9m plus 4. Okay. So now, moving forward from here, what do we get? Well, we can write this as 1/2. There's a couple different ways to do this, actually. If you go 9m minus 4 and negative 9m plus 4, it looks like a difference of squares, but not quite. We got a little bit more to go. So you get negative 81m squared. And then we'll have a plus 36m and another plus 36m. So that's going to be plus, in this case, it'll be, so we have plus 36 plus another 36. That's going to be 72m. And then minus 16. And an easier way to have done that is we could have written this as 9m minus 4 and pull that negative symbol out in front. So you're just actually squaring that term. So now, why is that important? So you have 81m squared plus 72m minus 16, all divided by m. So now we have a good equation for us. Let me see if I can taper this off. Okay, so a of m equals 1/2, and then we have 81m, when we simplify that, plus 72 minus 16 over m. Okay. So now let's take the derivative. So a prime of m. Notice that gives 1/2. Derivative of 81m is just 81. 72, that derivative is 0. Minus 16 over m. That's 16m to the negative 1. So that becomes, derivative of 16 over m is 16 times m to the negative 2 times negative 1. So that becomes plus 16 over m squared, essentially. Okay, so now what do we do with that derivative? Well, we set this whole thing equal to 0, so 0 equals 1/2 81 plus 16 over m squared. Notice the 1/2, that doesn't make any difference whatsoever. You can multiply both sides by 2, it gets rid of that. And so what we have then, subtract 81 over to the other side, you get negative 81 equals 16 over m squared. Multiply both sides by m squared. Did I make a mistake there? Yeah, I must have made an error here real quick. Hold on, I gotta go and backtrack just slightly. Okay. So, and the reason why was I saying I think I made a mistake? Well, notice you have m squared equals negative 16 over 81. You can't take a negative, a square root of a negative number. So I might have made a minor error in some of the simplifying here. So just let me double check real quick. Where did that occur? And this is good to see because it does happen. We have these little minor algebra errors. Okay, so let's start off plugging in x equals 0. So we had mx minus 9m minus 4. So we had negative 9m plus 4 was our y value. That seems to be good. Ooh, that's not good. Okay, that should be better. In our second case, plug in y equals 0. So when we added that on over, we had 9m minus 4 equals mx. So 9m minus 4 divided by m. And that was good. And then when we did 9m minus 4, negative, and then we had another 9m minus 4. So that would be 81 m squared minus 72m plus 16. I think I see the mistake here. Notice when I did this, I was supposed to have a negative distributing times the 9m, and so that should have been a negative 81m squared. So that makes this negative 81m. That makes this negative 81 right here. And so that means since this is negative 81, we add it over to the other side, and there's our error. And that's a good check because we know from our visual that, hey, we're going to have a nice answer in terms of what's going on. So back to where we were. So we get 81m squared equals 16, or m squared equals 16 over 81. Okay, so we're back to the right spot where we need to be. So now we take a square root. And notice you're going to get m equals plus or minus the square root of 16 over 81, which is equal to the plus or minus, that should be 4 over 9. Now you might be saying, well, wait a second. We already kind of looked. It has to be the negative. And that's right. We can't have anything having 0 or above for the slope. So when we're actually checking this, just to make sure that that is a minimum and not in fact the maximum, we'll have negative 4/9 for our m value, and we want to have a prime of m right here. We know that it equals 0 here. We just have to make sure that it goes, if it's going to be a minimum, it has to go from decreasing to increasing. So plugging in that value into our 1/2 negative 81 plus 16 over m squared, my strongest suggestion would be try negative 1. When you plug in negative 1, notice you get negative 81 plus 16. That's a negative number. Okay, and then pick a number really close to 0. So for example, well, let's try 1 over 16. Or negative 1 over 16. That would probably do the trick. So notice that becomes 16 squared, which is much larger than negative 81, so that would actually be a positive in that case. So it goes from decreasing to increasing. So what we need to do is find the equation of the line through the point. So this is in fact a minimum. And so the line that we're looking for is y equals negative 4/9 x minus 9 times negative 4/9 plus 4. So notice we have negative 9 times negative 4/9. That's going to be plus 4. So you get y equals negative 4/9 x plus 8. And that is our final answer. Okay. Hopefully that made sense. And you got to see a little mistake along the way. That happens. Those happen quite frequently in math. And that's what we're looking for, is trying to be able to find a solution when we do have something, this doesn't quite seem right. So, okay, moving forward. Where are we going here now? Continuity. So in continuity, you need the left-hand limit to equal the right-hand limit if there's any points of where we have to worry about. And so in this case, there's 2 points, or actually 2 points, I should say, 2 equations with 1 point. We need the left-hand limit to equal the right-hand limit. In other words, what does that mean? Well, we can plug in 2 into either equation, and they need to be equal. So, and where are we plugging them in? Well, we're plugging them in for the x. So b squared, you have 2 minus 1, and then plus 3b times 2 equals b times 2 plus 5. So what happens here? Well, we have b squared plus 6b equals 2b plus 5. So b squared plus 4b minus 5 equals 0. And I believe that works out nicely, right? Can't we do b plus 5 and b minus 1 equals 0? So yeah, b equals negative 5 and positive 1. And that'll do the trick. And notice when you plug in 2 now, you would have 2 values that are equal. And there's a continuity problem for you. Okay, last but certainly not least, unless you all have questions. If you have questions in particular, I'll try and answer them as they kind of come in. Find all the values C that satisfy the conclusion of the mean value theorem for f of x equals 10x times the square root of x plus 9 on the interval negative 9 to 0. So what does mean value theorem state? Well, it says there exists a C in the interval. And I should be careful. It has to be continuous. So you have this function is continuous in the interval negative 9, 0, such that, so that was a little caveat I kind of glossed over, but you do need that continuity, such that f prime of c equals, goes f of, in this case it would be 0 minus f of negative 9 all over 0 minus negative 9. Well, in this case, what is f of 0? Well, notice you plug in 0, and that 10 times 0 will make that whole thing 0. And f of negative 9, you get 10 times negative 9 times the square root of negative 9 plus 9, but that's the square root of 0, so that's also 0. So you have this thing as 0 minus 0 all over 0 minus negative 9. So this thing equals 0 is what we want f prime of c to equal. Okay, well f prime of c, well we'll need f prime of x in order for us to look at that. So f prime of x, what does that equal? We need to use the product rule, so that goes 10 times the square root of x plus 9 plus 10x times, well, that would be 1 over 2 times the square root of x plus 9. Okay, and so, oh, by the way, when we had this equal to 0, that actually is a special case of the mean value theorem. It's called Rolle's theorem. So if you ever hear Rolle's theorem, it's just a special case of the mean value theorem where both of those values are equal. And in this case, they even equal 0. So now moving forward from here, we want to try and find f prime of c. So f prime of c, just plug in c for everything. 10 times the square root of c plus 9 plus 10c. Let me write it this way. Let's get 10c over 2 times the square root of c plus 9. And that has to equal 0. So we're solving for c. So let's move that second 10c and then 2 square root of c plus 9 over to the other side. So you get 10 square root of c plus 9 equals negative 10c over 2 square root of c plus 9. Multiply both sides by the denominator and you'll all of a sudden get oh, and by the way, we could have canceled off and make it 5c if we want. It's not necessary though. So we get, what would that be, 20 times c plus 9. Or actually, let's keep it as 10. Let's make the other side 5. That probably would be easier. Equals negative 5c. And so moving forward from there, what do we get? We get 10c plus 90 equals negative 5c. So 10c let's add the 50, well, let's make it 90 equals negative 15c. And so notice if you have c equal to 6 or negative 6, you'll end up getting your answer, right? So c equals negative 6 is our solution. We got to just make sure it's not an extraneous solution. We didn't pick up a root when doing that squaring thing. And it works real quick. It doesn't take too long to see. You plug it in, you get 10, and then you have that negative 6 times that, and 2 square root of 3, and then 10 times the square root of 3. So it works out to be the same song and dance is what's going on there. Okay, so we find our solution to the mean value theorem, and we've found our conclusion to the final exam review. This doesn't mean this is all the material that'll be on there. If you have any other questions, I don't see any popping up right now. If you do, just let me know, and I'll be happy to answer them. Good luck coming up on that final, and I hope you all kick butt and take names when it comes time for that.